Chapter 5. In this screencast, we explore the topic of rate of change. We begin by discussing relationships between variables. The example below illustrates how functions are used to study relationships between variables of current interest in our world. In order to describe and understand real-world phenomena, we frequently need to understand how changes in one variable can lead to changes in another variable. Of course, if two variables have nothing to do with one another, then changing one variable will have no effect on the other variable. However, we're going to focus on variables that are in fact related. We want to know how changes in an independent or input variable will lead to changes in a dependent or output variable. So let's look at example 5.1. Recall from Chapter 3 that 19.37 pounds of carbon dioxide are emitted for every gallon of gasoline burned. So suppose a person drives a car having a fuel efficiency of m miles per gallon. Let's let C represent the pounds of carbon dioxide that would be emitted per mile. Let's look at part A. Which variable would be the input or the independent variable, and which variable would be the output or the dependent variable? Well, since the amount of carbon dioxide emitted depends on our fuel efficiency, we would expect that M would be our input or our independent variable, and C would be our output, or our dependent variable. So the value of C depends on the value of M. Now let's look at part B. Use your plausible estimation skills to determine a function relating the two variables M and C. Well, since C is our output, our function should have an equation of the form C equals, and then the right-hand side will involve our formula. This will involve M, and we'll have to figure that out. Let's begin by looking at the units of all the quantities that are involved here. First of all, there's M. M represents our fuel efficiency. In other words, M miles per 1 gallon of gasoline. C represents our carbon dioxide emissions. So C calculates the number of pounds that are emitted. C pounds are emitted for each 1 mile driven. And finally, the other quantity that we are told is that 19.37 pounds of carbon dioxide are emitted per gallon of gasoline. So we have 19.37 pounds for every 1 gallon of gasoline. So these are the three quantities that are involved here. Let's see if we can relate them using our plausible estimation skills. I'll start with the left-hand side of the equation. We have C pounds per 1 mile. Now we have to complete the right side of the equation. Since the left side of the equation has pounds in the numerator, I'm going to start with a factor on the right-hand side that also has pounds in the numerator. So I'm going to grab this factor right here, and I'll start with 19.37 pounds per 1 gallon. The left-hand side of our equation has miles in the denominator, but our right-hand side has gallons in the denominator. So we're going to want to multiply by another factor that will enable us to cancel the gallons out in the denominator and allow us to end up with miles in our denominator. And the factor we will want to multiply by will be this factor right here. except in order for us to cross out or cancel the gallons, we'll need to work with the reciprocal of this fraction. So I'll write 1 gallon over m miles. And now the gallons cancel, and the units on the left-hand side, remember, are pounds per mile. The units on the right-hand side are now pounds per mile also. If I rewrite this equation without the units, I arrive at C equals 19.37 divided by m. And this is our function equation that we will use for this example. Let's look at part C. Let's use the function we just calculated to complete the following table. Notice that in the first column of the table we have our fuel efficiency values. These are values of m. And the second column in our table has carbon dioxide emissions in pounds per mile. These are C values. So if we start by taking the number 15 and we substitute that into our function for m, we arrive at a C value of 1.2913 approximately, rounded to 4 decimal places. If we substitute 35 in for our function for m, we arrive at a C value of 0.5534. It's worth pointing out before we move on that as we increased our fuel efficiency, notice what happened to the emissions. As the fuel efficiency increased, you can see that the emissions have decreased. Now let's move on to part D. Suppose that you trade in your car that drives 15 miles on a gallon of gasoline for a car that drives 35 miles on a gallon of gasoline. So really you're going from this value to this value. Determine the total change in gas mileage and the total change in emissions, and be sure to give the units. Delta M stands for the total change in the mileage. Recall that when we calculate the total change in a variable, we take the final value and we subtract the original value. In this case, the final value is 35 and the original value is 15 because we went from 15 to 35. If we subtract, we arrive at 20 miles per gallon, and I'm going to abbreviate that MPG. So to interpret this change, we can say that we can drive an additional 20 miles on each gallon of gasoline by switching our car from a fuel efficiency of 15 miles per gallon to a fuel efficiency of 35 miles per gallon. Now let's calculate the total change in the emissions. Again, we take the final value and subtract the initial value. And when we do that, we arrive at a negative value in this case, negative 0.7379, and this is pounds per mile. So in other words, we emit 0.7379 fewer pounds of carbon dioxide per mile than we did previously when we owned a car that had a fuel efficiency of 15 miles per gallon. Now let's go ahead and look at part E. Calculate the ratio delta C over delta M, and then round your answer to 2 decimal places, and be sure to give the units. So we're going to take our emissions that we our change in the emissions that we calculated, and we're going to divide by the change in the miles. If we do the division, let's see, we have negative 0.7379 0.79 pounds per mile divided by 20 miles per gallon. If we work this out, we find that we arrive at negative 0.04. I'm going to write this in a fractional form over 1. In terms of the units, we still have pounds per mile in the numerator, and we still have miles per gallon in the denominator. Now let's explain in practical terms what the ratio delta C over delta M says about how the emissions change as the gas mileage is increased. Well, let's go and look up at our fraction above here. The denominator represents the change in mileage. So we have a 1 mile per gallon increase in our mileage, or in our fuel efficiency, and the numerator represents the change in our emissions. So our emissions are dropping by 0.04 pounds per mile. So if we put together these two changes, what we conclude is that for each 1 mile per gallon increase in our fuel efficiency, the emissions, the carbon dioxide emissions, decrease by about 0.04 pounds for every mile. So let's write that down. For each 1 mile per gallon increase in the fuel efficiency, and this is between 15 and 35 miles per gallon. So in that range, within that range of fuel efficiencies, for each 1 mile per gallon increase in our fuel efficiency, the carbon dioxide emitted drops by about 0.04 pounds per mile. Okay, let's move on to the next part. Shown below is a graph of our function. First, notice that M is on the horizontal axis because it's the input, and C is on the vertical axis because it is our output. Also note that the graph decreases. It has a decreasing trend as you move from left to right. This should make sense because we noticed above that as the fuel efficiency increases, in other words, as we move to the right, the emissions decrease. So as we go to the right, we should expect the emissions to drop. You can also notice or locate on the graph the two total changes that we calculated above. For example, 15 miles per gallon would be right there. 35 miles per gallon would be right there. And the change in our fuel efficiency is the difference of these two values. So if I subtract these two values, I get the 20. That's the delta M. So delta M on this graph is really represented by this distance between 15 and 35. We can also locate the change in the emissions. If I start at 15 miles per gallon and I go up to the graph, I hit at a point right here, and then if I go over, I arrive at the emissions that corresponds to a mileage of 15 miles per gallon. And we calculated that in the table at the top of the page. That was about 1.29 pounds per mile. So I'm going to go ahead and mark that. So here's that point, and if I go over to the vertical axis, that's the 1.29 pounds per mile. Similarly, if I look at the 35 miles per gallon and I go up to the graph, I get this point right here, and if I go from this point over to the vertical axis, I can find the emissions that correspond to a fuel efficiency of 35 miles per gallon. And we calculated that, again, in the table at the top of the page. That was about 0.55 pounds per mile. So I'm going to go ahead and mark that point and the corresponding value over here. So we have the two emissions. This was our initial emissions, this was our final emissions, and we subtracted them to calculate the total change. So really our total change is the difference between these two values. You can also think of it as the distance between those 2 points. So that is our change in emissions. Now, let's re-examine the sentence that we wrote above. For each 1 mile per gallon increase in the fuel efficiency between 15 miles per gallon and 35 miles per gallon, the carbon dioxide emitted drops by about 0.04 pounds per mile. Well, let's see if that makes sense on our graph. If this sentence is correct, then it would mean that each time we start at a point on the graph between the 15 miles per gallon and the 35 miles per gallon. So if I start at a point in this range here, and then I move 1 unit to the right, which corresponds to a 1 mile per gallon increase in my fuel efficiency, if we do that, then the graph should fall by the same amount, namely 0.04 pounds per mile. Is this what we actually see happening? Well, first, notice that the graph drops faster here than it does here. In fact, as you look at the graph from left to right, it falls more dramatically, and then as we move to the right, it slows in its fall. So it's falling faster here than it is here. To indicate this further, notice if I start at this point right here, if I increase my fuel efficiency by 1 mile per gallon, and that means I move 1 unit to the right, the sentence above says I should drop the emissions by about 0.04 pounds or per mile, or on the graph 0.04 units. So if I went this direction by 1 unit, then I should fall by 0.04 units. Would that same thing happen if I started here? If I started here and went 1 unit to the right, do I still fall 0.04 units? I think you would say the answer is no. Over here, we might fall actually more, perhaps, than 0.04 pounds, but over here, maybe we actually fall less than 0.04 pounds per mile. So it appears that our interpretation above, in other words, the sentence, is not quite correct. We should cross out the word about. So let's go ahead and do that, because that doesn't seem to be what we're seeing. So if that's the case, if this is not quite correct, then how should we interpret the ratio? Well, how did we calculate the ratio in the first place? We took the total decrease in emissions, delta C, and we divided it evenly among the 20 extra miles that we can drive on a gallon of gasoline by switching cars. If we do this, what we get is the average drop in the emissions for each 1 mile increase in our fuel efficiency. So we should go back to our practical interpretation above and make a change. So instead of saying that the carbon dioxide emitted drops by about 0.04 pounds per mile, the correct interpretation is to say it drops by an average of 0.04 pounds per mile. Again, if we refer back to our graph, if I just look in this interval here, every time I move to the right 1 unit, the amount that the graph falls is always different. If we look to the left, the graph falls considerably more than if we look over here to the right. If I could average these drops over this whole range, if I could calculate the average drop, that is the 0.04. This represents the average drop in this range every time I start on the graph and move 1 unit to the right. Okay, let's look at part G. In this part, we're going to estimate the same ratio, delta C over delta M, but in this case, we're going to do it when the fuel efficiency is increased from 30 miles per gallon to 50 miles per gallon. And again, we'll give our answer rounded to 2 decimal places. And we will explain in practical terms what this ratio says about how emissions change as the gas mileage is increased. So as we did before, we'll start by making a table of M and C values. Now in this case, our fuel efficiency is going from 30 miles per gallon to 50 miles per gallon. If we take these 2 fuel efficiencies and we substitute them back into our function equation, we can calculate the corresponding emissions in pounds per mile. And what we arrive at is 0.6457 and 0.3874. As before, notice that as the miles per gallon increases, in other words, as our fuel efficiency increases, notice that the emissions decrease. Now let's go ahead and calculate our ratio. So we have to take the total change in our emissions. Remember, we are going from 30 to 50. So these numbers correspond to our initial values, and these correspond to our final values. To calculate the change in the emissions, I take my final value and I subtract the original value. Similarly, I take my final value for the fuel efficiency and I subtract the initial value. When we perform these subtractions, we arrive at 0.0129, which, when we round to 2 decimal places, would give us negative 0.01 pounds per mile over 1 mile per gallon. Now let's go ahead and give a practical interpretation of what this fraction is conveying. So the denominator, again, represents the change a change in the fuel efficiency. So we are increasing our fuel efficiency by 1 mile per gallon. The numerator represents the corresponding drop in the emissions when the fuel efficiency has been increased by 1 mile per gallon. So the fraction tells us that for each 1 mile per gallon increase, as long as we're staying in this range, the emissions will drop by an average of 0.01 pounds per mile. Let's go ahead and write that in. So for each 1 mile per gallon increase in the fuel efficiency, between 30 and 50 miles per gallon, the emissions decrease by an average of 0.01 pounds per mile. Notice that this value, 0.01, is less than the 0.04 pounds per mile decrease that we saw on the previous page. Why is this? Well, in this example, we're looking at the range from 30 to 50 miles per gallon. In the previous page, we were looking at the range from 15 to 35 miles per gallon. So this range, if you look at the graph, this range is further to the right on the graph, in an area where the function's graph is not dropping very quickly. So we would expect the average drop in this range to be less than the average drop in emissions in the range from 15 to 35 miles per gallon, and that's what we're seeing in these numbers. We conclude this example with a couple of notes. First of all, the values of the output variable C decreased as the values of the input variable increased. Now that fact is what caused us to see this downward trend in the graph. We call this kind of a function a decreasing function. So a decreasing function is one that decreases or goes down as you go from left to right. Secondly, the ratios that you estimated in parts E and G, in other words, the delta C over the delta M, these ratios, they measure the average rate of change of carbon dioxide emissions over different fuel efficiency ranges. So in part E, we looked at the fuel efficiency range from 15 to 35 miles per gallon, and then in part G, we looked at the range from 30 to 50 miles per gallon. So this ratio right here in both of those ranges would be called the average rate of change of the carbon dioxide emissions over those ranges. So what we need to do now is generalize what you've seen in this last example. So in the general context, we won't be working with the letters M and C. In general, people will work with the letters X and Y. You'll notice this in many algebra texts. So the letter X is playing the role of the input, and the letter Y is playing the role of the output. So you can think of the M as like an X, and you can think of the C as like a Y. M is input, C is output. X is input, Y is output. So in our general case, imagine you start with a function f. So you've got F, you've got the input X, and you've got the output Y. Okay, looking at the first bullet. If increasing the X variable causes the output, the Y variable, to increase, then we say that the function is increasing. So let me show you a picture of this. So imagine you have your X, you have your Y, your input and your output. If increasing X causes your output to go up, that's going to give you a trend that generally looks like this. That's what an increasing function will look like. Now on the other hand, if increasing the X variable results in the output variable Y decreasing, then we have a decreasing function. That's what we saw up here. Our input variable was getting bigger, meanwhile our output variable was decreasing. So this is a decreasing function. This is what an increasing function looks like. Now let's talk about the idea of average rate of change in general. If you recall from our last example, when we calculated this ratio right here, and I'm going to back up for a moment, when we calculated this ratio, we started with a table of values. We started with one input-output pair and another input-output pair, and we used these two input-output pairs to calculate the total changes and then ultimately the ratio. So now we're going to do this in general. So suppose that you have two input-output pairs. So x1, y1 is one input-output pair, and x2, y2 is another input-output pair. And let's just suppose that the x1 is smaller than the x2. So this would be like our initial amount and our later amount. Then the average rate of change of the output variable with respect to the input variable x over this interval, so this would be like our range in the fuel efficiencies, like the 30 to the 50, for example. But the average rate of change is the ratio of the total change in y, in other words, the total change in the output, to the total change in x, in other words, the total change in the input. In other words, the average rate of change is calculated by taking the total change in the output, remember that's what we did here, total change in the output, divided by the total change in the input. That's what we saw here. We were dividing by the total change in the input. In terms of the letters, x and y, it's the change in the y variable divided by the change in the x variable. And remember that total changes are always calculated by taking the final amount minus the initial amount, final amount minus the initial amount. The average rate of change measures the average increase or the average decrease in our output. Think of our emissions. It measured the average decrease in our emissions for each 1 unit increase in X. Thinking back to our example, for each 1 mile per gallon increase in our fuel efficiency. And this would be true in some range between X1 and X2.